Okay, let's talk about linear functions. So for linear functions, the average rate of change is constant over any interval, right? Doesn't matter the length of the interval. You can make the interval like 100 values long, right? And you're still gonna get the same number. Um, so no matter what 2 points you pick, where on the graph you pick, you are always gonna have the same average rate of change. So let's calculate this. Here we have an example problem. Find the average rate of change for f of x equals 2x minus 7 from x equals 3 to x equals 6. So some of you watching might already know the average rate of change, but just in case you don't, we're going to plug this in. So let's find f of a first, which is, it doesn't matter what order you do it, and you can do 3 first. So let's find f of 3. So we have 2 times 3 minus 7. So what's 2 times 3? That's 6 minus 7 is -1. Okay. And now we're going to have f of 6, which is 2 times 6, or sorry, let me write that down. 2 times 6, which is 12 minus 7. What's 12 minus 7? That is 5. Okay. So now, let's say that this is A and this is B. And our equation from earlier, our formula from earlier was f of B minus f of A divided by B minus A. So if this is our B value and this is our A value, let's plug that in. So we have f of B, which we got was 5, minus -1, which is f of A, and that's going to be divided by B minus A, so 6 minus 3. Okay, now let's solve this out. 5 minus a -1, that's going to become 5 plus 1, which is 6, divided by 3. 6 minus 3 is 3. 6 divided by 3 is 2. So our average rate of change is 2 over that given interval. But that's, since it's a linear function, that's going to be the same no matter what points we pick. We could have picked 3 and like 200 as the other x value, and you're still going to get 2. And notice how this 2 right here comes right from here. The slope. The slope is the average rate of change. So we're already given 2 up there. So honestly, if you really didn't want to calculate anything, you can just look at that and be like, oh, the average rate of change is 2. It says right there. That's the slope of the graph. That's how you can find that out for linear functions. Now let's talk about quadratic functions. So here I kind of squished this a little bit, so we're gonna have to work up here and use some of the space from the last problem. So for quadratic functions, the rate is not going to be constant, because recall a quadratic function looks kind of like this, and that's not really a straight line, right? It's not changing at a constant rate. This slope right here, as the graph is kind of turning around over here, it's getting flatter out. That slope's going to have a less magnitude than up here, because this is coming down steep, right? Much steeper up there, so the slope is going to have a bigger magnitude. So for quadratics over here, note that the rate of change is not constant, but the change in rate is constant. So we're going to talk about that a little bit later, but we have an example problem over here. X squared minus 3x. So we're just going to do the same thing. We can use the same formula. We're going to plug in g of 1. And that's going to be 1 squared minus 3 times 1. Okay, let's solve that out. That's going to be, what's 1 squared? That's 1 minus 3 times 1. That's 1 minus 3. That's -2. All right. And then now g of, let's find the other one, g of 4. That's going to be 4 squared minus 3 times 4. Okay, what's 4 squared? That's 16. Minus 3 times 4, which is 12. That's 4. Okay, same formula from earlier. F of b minus f of a divided by b minus a. We're going to do the same exact thing. So our b value, we're just going to do that and that. I like picking the bigger number as the b value, the bigger x value, so that we don't end up, messing with negatives. So our b was, this is a, this is b, that was 4 minus negative 2 divided by 4 minus 1. Okay, cool. What's 4 minus negative 2? That's 6 divided by 4 minus 1. That's 3, 2. So we got the same. This problem actually ended up being the same average rate of change as the linear one from earlier. But if you were to pick another set of different points, well, I guess I could just said the same thing twice. If you picked another set of points, you'd get a different answer. Okay. Let's talk about concavity. This is going to be important for AP. So, concave up and concave down, right? And you might be asked to find concavity from a table of values or a graph. Okay, let's talk about this. When the average rate of change is increasing, it is going to be concave up. When the average rate of change is decreasing, it's going to be concave down. So let's look at the first graph over here. We have a linear graph. Is the average rate of change increasing or decreasing? Well, this is the linear graph. The graph is just a straight line. And we know from linear functions that the rate of change is constant over any interval. So the rate of change is not going to be increasing or decreasing. So this actually has no concavity. Okay. Let's do some blue, actually. Okay. So it's going to have no concavity. Now, what about this one? If we look at the tangent lines of this graph, tangent lines are basically like the straight lines that come off the graph. Notice how the slope down here is kind of like this, right? It's kind of a flat slope, right? So that's not going to have a really big value. But notice how as the graph goes up here, the slope is now going like this. So our slope is increasing, and the slope is average rate of change, right? So the average rate of change is increasing in this case. So that's going to be concave up. And as you know, as if our graph opens upwards, that's concave up. It makes a U shape, and that's basically the half of a U. Okay. Over here, concave. This one is going to be, notice how our slopes are actually, decently steep at the beginning, but now we're kind of flattening out as the graph goes this way. So as our slopes are decreasing in value, our average rate of change is decreasing. This is going to be concave down. And concave downs make a frown. And this graph is kind of going down like that. Okay. Now, you might be asked to determine concavity and function type from a table. So how do I do that? Okay. Well, these are, notice how on this side we have equal length input intervals. So as we go from 1 to 2, how is this changing? This is increasing by 2, right? We're going from 2 to 4. Okay, how about from here to here? 4 to 6, okay, that's 2 again. 6 to 8, that's 2 again. And 8 to 10, that's 2 again. So this function is linear, right? Because over any length interval, the average rate, notice how these are equal length intervals, right? But even if we go from 1 to 4, the average, it's still 2. If you want to calculate that out, that's going to be, what? 8 minus 2, that's 6. Divided by 4 minus 1, that's 3. 6 divided by 3 is 2. So you're still going to get 2 either way. So if we want to write that into a sentence, this is linear because over any length interval, the average rate of change remains constant. And what do we know about linear functions? They have no concavity. And that's because the average rate of change remains constant. Okay, what about the next one? So here we have consecutive equal length intervals again, right? Because we're going from 3, this is 3, blah, blah, so on. They're all 3 apart. Okay, but let's look at what we have in the table. 2 to 5, okay. So that's increasing by 3, right? But how do we determine average rate of change? That's the change in the y values over the change in x's, change in outputs over change in inputs. So the outputs, these are increasing by 3, and that's also being divided by 3, right? Because change in output is 3 over 3. Okay. Let's look at the next one. That's 5 over 3, right? Because they're increasing by 5, still dividing by 3. The next one is going to be, now we're going by 7. Still, the inputs are over 3. And what's the difference between that? That is 9. We're increasing by 9 over 3. So now, let's talk about the value of these. So, what do we notice about these? These are all different, right? Our average rate of change is increasing over all those intervals. So this is actually going to be quadratic. Because over equal length input values, because these are all spaced 3 apart, right? So over equal length input values, the average rate of change, and this is something that you want to pay attention to. How are these separated? How do you get from 3 over 3 to 5 over 3? You add 2/3, right? How do you get from 5 over 3 to 7/3? You add 2/3. How do you get from 7/3 to 9/3? You add 2/3. Notice how the change in the average rates of change are linear, right? That's constant, right? So that's how you identify a quadratic. So this table of values depicts a quadratic function because over equal length input values, the average rate of change is linear, right? And what's the concavity? Concave up, because if we just look over here at how our average rates of change are changing, they're increasing because the average rate of change over equal length intervals is increasing. And that basically sums up AP Topics 1.2 and 1.3. So here's the key things that you need to know about. Average rate of change is the change between 2 points. Instantaneous rate is a change at 1 point, and you approximate it using tiny intervals that are nearby. Linear functions have a constant rate of change, and quadratic functions, they have a rate of change that doesn't stay the same, but it changes, but the actual rates change in a regular, steady way, as we saw earlier in that table. If you look at equal length intervals, the change in rates follows a linear pattern. And concavity is determined based on how average rates of change change.